And I would like to go over to our last speaker, Minne Heringa from KWR Water Cycle Research Institute.
Well, thank you, Chairman. I would like to introduce to you today some target values that we have developed, which can be useful for the analytical chemists and the treatment engineers among you, and also for us toxicologists. And I'll start at the beginning. When we're talking about the chemical water quality of drinking water, legislation requires the producers to make drinking water that does not contain any harmful compounds in concentrations that are harmful in the drinking water and harmful for consumers. And for that reason mainly, about 15 compounds or groups of compounds have been put down in legislation, for example the EU Drinking Water Directive, with limit values, so the maximum concentrations. But there's also a general perception that the drinking water should be pure. It should not contain any contaminants really, especially with consumers. They are very sensitive to these kinds of messages. It's not only consumers that think this. Also, this has also been used in legislation. For example, the pesticide limit value put down in the EU Drinking Water Directive was not based on a health protection, but based on the perception that it should not be, these compounds should not be present really in drinking water. They should not be detectable. And in 1980, when this limit value was set, the detection limit was 0.1 micrograms per liter, and this was then set as a limit because then the concentrations below that would not be detectable. Well, now we face some new challenges. New contaminants continue to keep emerging, and as we encounter as toxicologists, very often the risks of these compounds are unknown. We do not have access to toxicity information, so we cannot make safe limit values for these compounds. And then the analytical technologies have also improved. For example, with this pesticide detection, the detection limits have gone down to about 10 nanograms per liter now. So now virtually anything can be detected in drinking water, and even when we saw in the presentation of PIM, we can come down to 1 nanogram per liter for the drugs of abuse. So with these detection limits going down, we see more and more chemicals being present in the drinking water. Now, of course, on the other side, the new technologies are also improving, so the removal of these compounds is also becoming better and better. But still, the removal is not complete, and sometimes the costs of ever-increasing removal are also very high. So we come to this dilemma that actually this perception that we don't want the chemicals to be detectable in the drinking water is not really realistic. We cannot achieve it very well. So a question we sat down to answer was at what levels of contaminants do we think the drinking water is still of an impeccable quality? And these levels were meant to serve to protect the human health, also to keep the consumer acceptance, so we have a good, solid story to tell them, and also to make to serve as a framework for these new technologies on the chemical analytical side and on the treatment side, going to the question how far should these improvements go? Do we ever go ever increasingly down to ever lower detection limits and higher removal efficiencies? Well, the basis for these levels that we were developing was the TTC. Hey, I missed something. TTC for no, I do miss a slide. This should be the slide before. The basis for these target values that we were developing is the threshold of toxicological concern, the TTC. And this is a threshold that was developed actually for food additives. developed by ILSI, a European Institute, because in food there are also many additives in the food that are at very low concentrations, and they asked the same question: do we have to determine risks for all of these very small levels of additives in the food, or is there a certain concentration at what we can waive any risks for the human beings? And what they developed was a threshold, a concentration in the food below which no compound would be expected to give any health risk. And the way they did this is to collect all the toxicity information, and the toxicity information was in the form of dose-response curves, like here. You have a dose on the x-axis and the toxicological effect on the y-axis, and typically they have this curve form. And they collected all this information for all compounds available, put these together, and well, schematically, then they decided at what dose no compound of this set gave an effect anymore. So then for other compounds you can also expect they do not give an effect as well. Now we go back. So they developed these for food additives. Well, we are talking about drinking water. The consumption is a little bit different. So we translated the TTC for food into a TTC value for drinking water. And we did this by taking the TTC for food and then taking an allocation factor of 10%, because in the dose you get daily from drinking water is not as high as you get from food or maybe from breathing in air. So it's only 10% of your daily dose we generally assume that you get from drinking water. And then we divided it by a drinking water consumption of 2 liters per day. The TTCs for drinking water were then 10 nanograms per liter for genotoxic compounds. Genotoxic compounds are compounds that damage the DNA, and thereby they can cause cancer. And they can do this at very low concentrations already. So that's why these are the lowest, they have the lowest TTC. Then there's a default TTC of 0.1 micrograms per liter. And then for certain chemical structures they found higher values. For example, organophosphates, they were found to be all safe already at below 0.9 micrograms per liter. And there were some exceptions as well. Steroid hormones, dioxins, methyls, nitrosamines, and some other examples were not included because they were found to be so toxic again that they would not fit into these TTCs. So we use these TTCs to derive target values, and the vision we had behind this for the drinking water quality of the 21st century, the Q21, was that these target values should not give human health risks, of course. Also, they should incorporate the vision that non-natural compounds do not belong in drinking water, like said before. And also we had a practical problem that we do find steroid hormones in the water, and we want some kind of value for those as well. So we wanted to include them too. Well, because of this second principle, we decided to use the TTCs. The TTCs, of course, protect for human health risks, but we put a cutoff at 0.1 micrograms per liter because we find that actually the compounds do not belong in drinking water. So finally, the target values we developed were 10 nanograms per liter for genotoxic compounds, and also we put this level for steroid hormones, and I'll show you why in a moment. And for all the other compounds, 0.1 micrograms per liter. Then we also thought, well, you can have 1,000 different compounds in your water, and they can all be just below this level, but if you add them all up, you have quite a high total load, of course. And we do have some chemicals giving mixture toxicity, so they have an added toxicity. So if you have all of them in your drinking water, you can have a higher effect than they have individually. So we also wanted to put a limit to the total contamination load. And this we put at 50 nanograms per liter for the genotoxic compounds and the steroid hormones. So you can have 5 compounds just below this level and still be safe. And the other compounds at 1 micrograms per liter. So then you can have 10 compounds just below this level and still be on the safe side. Well, just for your reference, I put some comparison to limit values. NDMA is a genotoxic chemical which has been found in water and in drinking water. And the limit set by the WHO is now 10 nanograms per liter. So this is comparable to this target value of 10 nanograms per liter for genotoxic compounds. The same for benzoate pyrene. And then for estradiol equivalents, estradiol is a steroid hormone which has hormone disrupting effects, and other compounds can have this effect as well. The RVM has set a provisional kind of alarm value or trigger value at 7 nanograms per liter. So this is the cumulative concentration if you would calculate all the concentrations and potencies of the compound back into what estradiol would do. So this is why we put the steroid hormones at 10 nanograms per liter as well. Pesticides, as I already showed, they are put at 0.1 micrograms per liter, so this correlates very well. PCBs correlate very well too. The sum of the PCBs are a little bit lower, but then of course there are more than PCBs in the drinking water. And benzene and vinyl chloride are examples where the limit value is actually higher than the target value. But this is logic. I mean, the target value is the lowest value where you can waive risks. And these are for the individual compound, they can be higher. So how can you use these target values then? It must be you must remember that these are not legally enforced. It's not the idea to have them put down into law, but these are aesthetic limits going further than the law. They are voluntary, just to have a kind of framework. We, as toxicologists, we can use these new contaminants, new target values when we find new contaminants and we don't find any toxicity information. And then we look at the concentration that has been found. If it's below the target value, we know there's no problem with human health. If it's higher than target value, still there doesn't have to be a problem, but we need some further study. We can't waive. Then for the analytical chemists, these concentrations can serve as a framework for how far should we go with our detection limits. And also for the engineers, this can serve as a framework for how far should we go with our treatment designs. And finally, managers can use these values as a lobby to regulators. They can say, hey, in our source water we find concentrations that are higher than the target values, and we don't want to put so much money into treating the water to make it acceptable and impeccable. So do something about our source waters. I have some examples of the use of these target values. The first example is with glucocorticoids. The glucocorticoids are a group of hormones which you can find, for example, in creams against eczema, and they're also used for anti-inflammatory responses. We detected them in drinking water sources. For example, in the Rhine at Lobit, where the Rhine enters the Netherlands, we found a maximum concentration of 2 nanograms per liter equivalents of the reference hormone. There were no limit values for these kinds of compounds, but so then we could use these target values for the steroid hormones which are 10 nanograms per liter for an individual compound and 50 nanograms per liter for the sum. Now, as we are talking about equivalence, so it's the total load of all compounds that have this effect, we have to take the sum, and we find that the concentration is below this sum. So we don't expect any health risks from these kinds of concentrations, and we can say the water quality will meet the quality target for these compounds then. A second example relating to the presentation of PIMP, the drugs of abuse. We have an analytical method going down to a limit of quantitation of 1 nanogram per liter. You could ask the question, do we need a higher sensitivity? Do we need to be able to analyze more? Well, the target value for these non-genotoxic compounds, because the drugs of abuse are not genotoxic, is 0.1 microgram per liter. So for individual compounds, this is certainly safe enough, sensitive enough. When we talk about the sum, because there are multiple drugs of abuse, the sum is 1 micrograms per liter. Now, if you have a limit of quantitation of 1 nanograms per liter, it means you would need about 1,000 compounds just below this level to reach the target value. And as I think we are talking about orders of about 1,000 different compounds in the water, so it's not 10,000s, I think, and it's not hundreds, it is in the order of thousands. I think this is just right enough to be able to detect the whole total load of possible compounds in the water. So then it is sensitive enough. We really do not really need to go further for the moment. Then a new treatment facility. For example, when a new treatment engineer goes to his management and he wants a new treatment design for a plant that has become very old, and he has some brilliant ideas of how this should look like with new technologies, better removal. The management board, of course, wants to know, is this really worth it, this investment of millions of euros? Well, then you can show that the contaminant levels currently do not meet the quality standards, or they do meet, but then the management board will, of course, say it's not worth the investment for the impeccable water quality that the producers want to deliver to the consumers. And if it's the case that they do not meet the quality standards yet, these managers can then go to the regulators and complain, hey, look at, I have to invest millions of euros here to make this impeccable water qualities because the source water is not of a good quality. So do you do something about the source water quality? So with that, I hope to have given you some idea of how these target values can be used, and I hope they could be useful for you. And I thank you for your attention.